All right, people's next unit, which is 8.4. So one thing you'll notice is that 8.4, 8.5, and 8.6, they kind of all go together. And even on the days, it says, we should do all three of those in one day. But I'm just going to do 8.4 for video notes, and we'll finish up the rest tomorrow. So this section is finding areas between curves expressed as a function of x. So what we've done so far is we found the area under a curve, right? So for example, like this, we found the area under this curve right here of f of x, just the blue curve that you guys see. So that curve, when you find the integral, you're basically finding this little green section. And then if you have a curve like g of x, like this red guy right here, finding the integral of g of x from 1 to 3 means that you're finding this little blue section. Well, now what if we wanted to find the area between two curves? So between two curves. Basically, what we would do is we're still going to use rectangular approximations, okay? So if you remember, for this guy, we used to think of Riemann sum, right? And go all the way down. We're still going to make rectangular approximations, except we're going to focus on the top function minus the bottom function. And what that does for us, what that will do for us, when you find the area of a region between f and g from 1 to 3, you do the top minus the bottom from 1 to 3 will give you this little pink area right here. And that is the same thing as saying the area under f of x minus the area under g of x, right? Minus this little area right here. And once you do that, you end up with this middle section. So by definition, the area of a region between two curves, if f and g are continuous from a to b, and g of x is less than f of x, so g of x is the lower function, or the bottom, and f of x is the top, for all x in a and b, then the area of the region bounded by the graphs of f and g and the vertical lines of a and b is the integral from a to b of the top function minus the bottom function. That's all it is. So when you're finding the area of a region between curves, you want to find the area of the region bounded by the graphs of y equals x squared plus 2. So let's take a minute and graph that function. Well, x squared plus 2, I know it's a quadratic with a y-intercept of 2, so I'm going to roughly draw it. I know that at 1, it's going to cross at 3, and at -1, it's also going to cross at 3. So here's my quadratic. And y equals -x, well, that's a linear function with a negative slope. And a y-intercept of 0, so there's that. And then from x equals 0, so there's x equals 0. And x equals 1. So where is the area between all of these curves? Well, The area between all of these curves is right over here. So we want to find the area of this shaded green region. Now, when we draw our rectangular slab, this is how you want to always kind of think about area between curves. You draw your rectangular slab. Because you are drawing it perpendicular from the top function, so there's our top function, here's our bottom function, right? And it is perpendicular to the x-axis, which means our bounds are from 0 to 1. So when you set up your integral, the area of that green section, right, is equal to the integral from 0 to 1, that's over the x-axis, of the top function, which is x squared plus 2, minus the bottom function, and we know that the bottom function is negative x dx. That right there is the integral to find the area of that shaded green region. And then you clean this up and integrate. So first we're going to do x squared. I'm going to rewrite this as x squared plus x plus 2, right, dx. So the integral is going to be x cubed over 3 plus x squared over 2 plus 2x from 0 to 1. And when you do that math, you've got 1/3 plus 1/2 plus 2 minus 0, right? So 1/3 plus 1/2, you've got 3, 4, 5, 5, 6, 7, 17 sixths. So that is the area of that green section between that top and bottom function. So next example is you have a region lying between two intersecting graphs. So in this previous example, the pink function and the green function did not intersect each other, but we were able to isolate that area using the two bounds of 0 and 1. So now with this one, a region lying between two intersecting graphs, let's look and see. So the first one function, find the area of the region bounded by the graphs 2 minus x squared. Well, this is a quadratic that is flipped down. I know that at negative 1, we're going to be at 1, and at 1, there it is. So you don't want a perfect graph. You just want a good enough graph to be able to graph it accurately, right? And then our second function, our g of x, is going to be x. So x looks like this. Okay, I want this to keep going so that we can see that intersection point. So we want to find the area region bounded by the graphs. So basically the area that we are looking for is right here. So the area that we are looking for is right here in this green shaded area, right? So you're always going to draw your rectangular slab, okay? Your small rectangle, the Riemann sum rectangle, from between the two functions. You have to touch the top function to the bottom function. So you notice that our rectangular slab is perpendicular to the x-axis. So that means our bounds are going to be between the x values. Now, they don't tell us what the bounds are, so we need to figure out these 2 points of intersections between those graphs. And how do you do that? Well, that's going to be basic algebra, if you remember. We know that these 2 points, to find the points of intersection, you set f of x equal to g of x to see where they are intersecting. So 2 minus x squared equals x. Now this is a quadratic, so it makes sense that we have 2 points here, right? So we got to solve it like a quadratic. So I'm going to move the x over. So that's going to be negative x squared. I'm just rewriting them properly, equals 0. And of course, how do you solve a quadratic equation? By factoring. I'm going to remove the -1 just to make my life easier when factoring. And you want to ask yourself, what are 2 values that multiply to -2 and at the same time add to 1? And that's going to be x plus 2, x minus 1. So x equals -2, x equals 1. And those are the 2 points of intersection. And it's happening at x equals -2 and at x equals 1. And the reason that those are important is because these are going to be the bounds of my shaded area. So now the area is going to be the integral from -2 to 1. And you notice that these are x values, which is why we would be drawing, ideally, right? You got to think of all of the rectangular slabs, the infinitely small slabs, are going from -2 all the way, from -2 all the way to 1 on the x-axis. So if these are x values, that means the functions are going to be with respect to x, and it's still going to be the top minus the bottom. So it's 2 minus x squared minus the bottom, which is x. And our change in x, or the width of each of these rectangular slabs, is dx. All right, and I will let you guys finish that up. The answer would be 9/2 once you integrate. A region lying between 2 intersecting graphs. Find the area of one of the regions bounded by the graphs of sine of x. So we know that sine of x is at 0. At pi over 2, we're going to be at 1. At pi, we are back at 0. At 3 pi over 2, we are -1. And like this, right? Now cosine of x is at 1, then 0, then -1, back to 0. So cosine of x looks like this. So hopefully you've noticed that find the area of one of the regions, right? Because sine and cosine will be going on forever and ever. And because they are periodic, they are, the areas of their intersecting parts are going to be the same. So let's just pick one area. I'm going to choose the area from here. I did not want that. I wanted the green. So right here. Now to figure out what these points of intersection are, so to find the points of intersection, You notice I'm not writing POI because we called point of inflection or inflection points POI long ago. So points of intersection, we're going to take sine of x and we're going to set them equal to cosine of x. Well, you have to remember the unit circle at this point, and you know that sine of x and cosine of x have the same signs in quadrants 1 and 3, right? So we know that when is sine of x equal to cosine of x? Well, that happens only at pi over 4 and 3 pi over 4. So we could have actually picked this area, but I know that this point right here is just going to be negative 3 pi over 4. It's the same thing as this point, which is 3 pi over 4. Okay, so it's up to you which points you use. It doesn't really matter. But once you find the points of intersection, the area is super easy. You're going from negative 3 pi over 4 to pi over 4 of the top function, right? When you draw your vertical slab right here, the top function is the green function, which is cosine of x, minus the bottom function, which is sine of x. And you integrate this with the given bounds, and you've got sine of x plus cosine of x from pi over 4, from negative 3 pi over 4 to pi over 4. And I'll let you finish up the rest of that answer. You should get 2 square root of 2 for the area. So 8.5, the only difference is finding the areas of curves expressed as a function of y. So if you just take a look at this example, it's basically, it's a function, but you notice that it's with respect to y and not x. So we'll do the rest of 3.5 and maybe 8.6 tomorrow. If we don't get to 8.6, that will be your homework. Okay? If you want to move ahead, you're more than welcome to use the QR codes for 8.5.